go to the cloud.
Just going to do the introduction and then.
Yeah. Then so that's first.
Next one. Okay, good morning, good afternoon, everybody. Thanks for coming. It's really a great pleasure to introduce today's GEOS distinguished lecturer. Professor Jiang is the Vice President of Nanjing University of Aeronautics and Astronautics in Nanjing in China. This is one of the most well-known universities, especially in the engineering area. And of course, Nanjing, for those that haven't visited, it's a very historic city in China with a very long history. And we are very happy. I know Professor Jiang for many years, and we work in similar areas. So it's a great pleasure to have the opportunity to welcome him to the University of Cyprus. And I should also say that the University of Cyprus has just signed a cooperation agreement with Nanjing University of Aeronautics and Astronautics, with the rector of the university and Professor Jiang just an hour ago. So we hope that this is going to open up new opportunities. Before we start today's GEOS distinguished lecture, let me just say a few things about today's speaker. He received his PhD degree in automatic control from Northeastern University in Shenyang, China in 1995. He has been a postdoctoral fellow, research fellow, invited professor, and visited professor in Singapore, France, USA, and Canada, respectively. Now he's a chair professor of Chang Kong Scholar Program in the Ministry of Education and vice president of Nanjing University of Aeronautics and Astronautics in China. Currently, he serves as senior editor of the International Journal of Control, Automation and Systems, associate editor of the editorial board member for a number of journals, such as the IEEE Transactions on Cybernetics, IEEE Transactions on Neural Networks and Learning Systems, IEEE Transactions on Industrial Informatics, and others. He's an IEEE fellow, chair of the Control Systems chapter in IEEE Nanjing section, a member of the IFAC Technical Committee on Fault Detection, Supervision, and Safety of Technical Processes. And his research interests include fault diagnosis, fault-tolerant control and their applications to helicopters, satellites, and high-speed trains. I should also say that Professor Jiang has been the principal investigator on several projects of the National Natural Science Foundation of China. He's the author of 8 books and over 200 refereed journal papers and conference papers. And he won the second class prize of the National Natural Science Award in China. So we are very happy to have him here today, and we look forward to this lecture. Thank you.
Okay. Yeah. Good morning, ladies and gentlemen. It's my great pleasure to visit the University of Cyprus and make a presentation in the GEOS Research Center for Excellence. I know the research center is very famous, in particular in the field of fault diagnosis and fault control, since the Professor Melis Lecapo is I think is world famous professor in that field. In fact, many of my research work is just follow you. I follow you to do some. And after I come back to China, I have a good collaboration with Professor Couple. We have already co-supervised several PhD students and postdoc. Okay, so it's my pleasure to introduce the research work of my team. The title of my talk is the adaptive fault diagnosis and reconfiguration control with flight control applications. This is the outline of my talk, including 4 parts. The first one is about the study motivation and history, etc. Then I will present the research work in my team about the adaptive fault diagnosis and photon control for nonlinear systems, switch systems, and the multi-agent systems. After that, I will give some application of the proposed method and technology to 3 typical flight control systems. That is the satellite, the hypersonic system, and the helicopter. Finally, give some research perspective in the future work. As you know, in the past decades, many accidents and disasters happened due to the occurrence of the fault. In this page, I just list a few. For example, in 1986, the Challenger space shuttle disintegrated due to the proper sealing detached. In 2016, F-15 Curl-based aircraft crashed while landing because of the flight control system fault. In 2018, the Cuban airline Boeing 737 crashed, also due to the engine fault. In China, in 2011, there's the Ningbo Wenzhou high-speed train rear-ended due to the signal fault. More than 400 people died and injured. So due to the such disasters, so speed of the high-speed train reduced, I think, a lot. Okay. But the country has recovered. So how to avoid this accident or disasters? The new technology, the fault diagnosis and photon control have been developed to ensure the safety and reliability for the faulty dynamic systems. This is the focus of our team. Since the fault diagnosis and photon control have a wide application background, so they have attract high attention by academic community. For example, the IFAC established the technique process for diagnosis and safety technique committee and have a conference held every 3 years. For me, I have attended the conference, Safe Police Conference, began from Washington because I went abroad at this time. And Cyprus, I know this hold is 2021. I intended to attend this conference, but because of the COVID-19, cannot attend. But 2 years later, so I'll come here to attend. And in China, we also very highlight Chinese community highlighted the safe process. So in 1997, Chinese Association of Automation established the similar community about the fault diagnosis. And every 2 years, we had a national academic conference. In 2011, in Nanjing, so our research team held such conference. So this is a broad diagram for diagnosis. So from this, you can see the fault can occur in the actuator, plant, and the sensors. So if fault occurs, the system performance may be degraded, and even the accident or disaster will be happen. So we must diagnose the fault as soon as possible, and based on the information of fault diagnosis, to reconfigure the fault to keep the system performance and basically keep the safety of the system. So this is some term about the fault. What is fault? What is fault diagnosis? What fault control? I don't want to go for details. So for fault diagnosis method, generally you can have two kind of method. One is so-called the quantitative method. Another is qualitative method. For quantitative method is based on the analytical mathematical model, adaptive estimation, model matching, filter, etc. For qualitative method is based on the knowledge and the data categorization, the bar graph. And on the other hand, fault tolerant control, in short, FTC, can also classify into two kinds. One is called the passive fault tolerant control, which is the idea is similar to the robust control. We're using the robust control structure to handle the fault. For such method, we know the limit of the fault. So when we design the controller at the beginning of controller, we consider the limit of fault. So this is called passive. It's an idea of it comes from the idea of robust control. Another FTC method is active fault tolerant control. For such method, we including the actuate the fault diagnosis and make decision and reconfigure the controller. So the two kind of. In my team, we research both two methods. Okay, in this page we list some books on this field. So the pattern and the for me is also in 2009, when I come back to China, I have published a paper on this in this domain. And after that, my student also has some books published in this field. Also, we list some papers. So from this, you can see the polycarbo have very high citation. So me also, because my group, I have nearly 20 faculties and more than 100 PhD students, only focus on the FTC, and so have a largest number of studies. And this is a summary of our team. So our team is engaged in the FTC and the FTC. So with application to the aerospace field. So we have obtained the fruitful theoretical result and also some practical experience. So this is a research result. We have published 15 books, mostly in the Springer, and published more than 200 international journal articles, including some top journals such as AAA, JGCD, and IEEE, and the IEEE TSC Automatic and IEEE TSST. And besides some theoretical article, we have also applied some invention patents, more than 50, and has authorized 35 invention patents. Now, today I want to focus on the adaptive fault diagnosis and the reconfiguration. This is adaptive fault estimation and accommodation. Yeah, is a fault diagnosis and fault control based on the adaptive techniques. The early work was done in 1990s. During the past 30 years, a series of research results have been attempted, including fault estimation and active fault control. So the fault estimation, so for such method, we use the adaptive observer to estimate the fault parameters. We're using the adaptive control approach to reconfigure the controller. So this is a block diagram. Compare with the previous one, the difference is See, we using adaptive observer for the diagnosis mechanism with adaptive control to reconfigure the controller. We have a several paper published in the Journal of Control and Decision. I think there's an associated conference, so-called CCDC. You have made a planned talk in this. In fact, this is the editor-in-chief of this journal is my supervisor. Is academician, also academic something. Now I will introduce the research work in the 4 parts. The first one is about the adaptive fault estimation and accommodation for nonlinear system. The idea is that for the continuous nonlinear system, we propose a new approach based on the adaptive estimation and active fault tolerant control with using the fault estimation information to accommodate the fault, to compensate the affected fault, to assuring the stability of the fault system. This is the the result. I don't want to go for details. So this is the model applying the nonlinear systems. So this FT is the fault, and the nonlinearity G is we design the fault estimation system, which is F hat. F hat is estimation of the fault. So based on the fault estimation, we can construct the active fault tolerant control. It can be seen in the composite controller, the FU1, the U1 plus the U2, and the U1 is the using the information of fault estimation. U2 is to stabilize the nonlinear term. This work is published in the IEEE. I remember in this paper I cite I think at least 3 papers of yours because you have done some pioneer work for diagnosis for nonlinear systems. I did this work originally in France with Marcel, Marcel Prof. But because of, for IEEE TSC, the review process is very long. When it's published, I come back to China. Okay, another model is about the switch system. Switch system is a series of continuous model under the discrete event Weasley. Many, in my opinion, many practical systems can be described by the switch system. For example, the advanced aircraft always fly in the large envelope. So it's very complex to model the flight dynamics in one model. So we always classify the large envelope into several small ones based on the flight height and flight velocity speed. So the whole flight dynamics can be modeled as a switch system. Another example is about the multi-body spacecraft switched configuration. It can be also described by the switch system. So for such system, the problem is besides continuous fault, which destroy the dynamics of the related models, also have discrete system will be changing the switching time or switching order. So this is difficulty for such system. So the objective is to the stability for switch system. Now we consider the such system. This is a continuous fault, deployed continuous fault. This is switching function. So difficulty is to keep the stability, so which required fast fault detection, fault identification, and accommodation. This is some idea for the continuous fault. So a local fault tolerant control mechanism is designed for each fault mode to ensure the stability of fault models. And then the switch law is designed to guarantee the stability of the whole switch system. So for the switch system, the fault tolerant control consists of 2 steps. For each fault mode, we design the local photon control. And then for the whole system, we need to design the switching law. So this is comprehensively accommodate the controller of each model and the switching law. In this topic, we have published several papers in Automatica and actually CST. And you know, the Hao Yang is my first PhD student. He's supervisor of Meng Jingkai. Now we consider the switch symbol for the discrete fault, because for the discrete this term describes discrete fault. Okay, this is a nominal switching law. This is a fault switching law. So the idea is we propose the adaptive switching law to estimate the changing rate of the time and the sequence. This is Hao Yang have a publication in actually TSC. We have an English book. I think maybe this first English book appear in the Springer, such handle the photon control for hybrid system. Now the third topic is about the fault accommodation for multi-agent system. So multi-agent system, complex large-scale system, which is formed by a large number of autonomous or semi-autonomous agents through the network communication. We list two examples, the IAI and the US Army MQ-8B, which can be described by the multiple agent system. So we have do some work about the fault accommodation for the multiple agent system. One work is the distributed fault estimation based on the switching topologies. So this one is the topology switching mechanism. This is switching topology. So based on this information, we design distributed fault estimation, and then based on the average during time. This is another PhD student, Dr. Ke Zhang, has done some work on this issue. For multiple agent systems, most difficulties is about the heterogeneous multiple agent system. Compared with the homogeneous multiple agent system, there has some difficulties or challenges. Challenges one is the heterogeneous multiple agent system, because they are different in the individual structure and the parameter. Even the physical state are different. So how to improve the accuracy of fault diagnosis by using the interactive information? So it's a very challenging problem. Another challenge is that when we do such issue, we find that nearly no result, no literature about such domain. So we want to is very limited literature can be referenced. This is some work, decentralized active photon control based on the integrate sliding model observed. This is Prof. Jiang. This is my PhD student. Is also I attribute cybernetics. We also have a server paper in the IEEE transaction on the industry informatics. In that server paper, we have, of course, some work of our team and other teams about the what we call the FTCC, fault tolerant cooperative control. Because this is for the multi-agent system, we must consider the cooperative control. There's some English book, there's Dr. Ke Zhang published a paper on the observer-based fault estimation techniques. Also, I want to present some work which is co-authored, which is by the Xu Yuhan, and which is under the co-supervision by Professor Policarpo. This is a FTC game using game theory to handle FTC for the network system. for such system, we have 3 layers. This is a human layer, which you have some consider some fault, asymmetric fault. This is cyber layer, which is maybe some cyber attacks. The physical layer, the physical force, for example, the actual fault, the sensor fault. So I have 3 layers. So we for such system, we consider the decision maker fault and the physical fault, and based on the different geometry, we design the photon control. The first one issue is about is called the zero-sum game-based passive for FTC for interconnected systems. So this is a zero-sum game inside each term. This is a graphic game among the subsystem. So this is play one is controller, play 2 is the fault. So this work is have been done before she came here. The IEEE TNAs, and then for the fault tolerant control, design the leader. This is cost function of the leader and the cost function of the follow of the leader and of the follow. Okay, this work had been done when he come here, co-supervised by the Professor Couple. This is using the stack back differential game approach. This work. So it's have 4 steps. So again, I don't want to go for details during the time limited. Using this shows the simulation result about the convergence of the estimation error and the system state. This is the multiple player pursuit evasion differential game with malicious pursuits. Is also IEEE TSC. There's some details. This is the strategy design. This simulation result. Okay, the second part. Third part is we choose 3 typical flight control systems: satellite, hypersonic, and helicopter, to demonstrate our approach. The first one is about the satellite. You know, the satellite is a control technique have been developed for many years and many results. But as I said before, the topic in my research team is focused on the fault detection and fault tolerant control. So many results for this one. It's about we interested in the identify the fault, isolate the fault, and realize the system reconfiguration. We have done some theoretical research and also developed the platform development. So this is some theoretical research. Okay, I don't want to go details. Just is the adaptive failure identification with self-stabilization ability. This is my larger PhD student, which is published in IEEE CST. This is semi-physical simulation platform for the fault tolerant control of satellite attitude control system. This is semi-physical. We're using such platform to demonstrate to verify the efficiency of our method. So this is the air flotation platform for detection of magnetic torque and momentum wheel. This is we self-developed reaction wheels and the magnet torques. And besides this, we also developed some satellite system control interface. This is a result of FTC by switching between 2 reaction wheels. From this, it can be seen after switching, the detection curve return to the threshold, and the attitude angle recover to the desired ones. This is about the FTC, FT, and FTC for the evasive satellite, about the initial interface and initial setting. This is, from this platform, we can show the altitude and trajectory, and including the angular velocities and the altitude angle, and the control totals very conveniently. So this is some simulation result. Okay, in this domain, we have obtained quite a few patterns, including the fault injection, fault detection, fault estimation, fault tolerant control for satellite altitude control. Is some specification. The second one is about the near space vehicle. You know, the near space, what it means near space? Near space is a new space, I think without well developed, located in the middle of the aeronautics and astronautics airspace. So it's a focus or is a hot topic. But the difficulty is that because there's a characteristic for the high maneuverability and complex nonlinearity and strong coupling uncertainty and the fast time varying. So they have raised high requirement for technology, for new technology for the fault diagnosis and the fault tolerant control. We chose this model, winded coin model. This is because the aerodynamics layout for such NSV model has a very good advantage. For example, it has a large lift drag ratio. Oh, this is a flow diagram of fault diagnosis of NSV. So see, this is for such model, we have fault injection, to slow the data accuracy and the interface interaction. We can design the fault diagnosis system, including the health management. So if there's a fault, we give alarm and reconfigure the flight control system. If normal, we continue the monitoring. This is the flow diagram of fault diagnosis for NSV. We have done some research work. We just list one. This is fault estimation and accommodation for NSV based on the adaptive technology. This is a block diagram. This work has been published in the IEEE TFS. Besides some street work, we have designed a platform because the data analysis method has some shortcoming. So we use the virtual technology because it has some advantages. It's very convenient to observe and control the effect and realize the evaluation. So we use the simulation verification. This is related to the Malaysian crater Vega. So it's used for the virtual development. During the three-dimensional models motion through the simulation of data of MATLAB. So this is a modeling. This is a key technology of modeling with craters, including LOD, DOF, and text model. And the function of the instrument is to display the information of altitude change of the aircraft. This is the wind transform. This have two models. One is fixed point, another is swivel. And for the mode of observation, we have several. We can from back view is a single channel. From multiple channel, we have view of right side, vertical side, and the front side. So this is a simulation result for the virtual platform. You see, this is from the back view. This is from vertical view. This is from side view. This is from front view. So the simulation result. This is to show the tracking performance with normal controller. Means it's no fault. We use normal controller, so you can see no tracking error. Exactly tracking can be achieved. So if fault occurs, we still use the normal control, you can see there's a tracking error. Okay? So if we use the photon control, we propose the tracking performance can be recovered. Okay, so the asymptotic tracking. Very convenient to see the result. Okay, the third application is about the helicopter. This is some hardware about the helicopter. This is hardware component and for the helicopter flight control system. This is some experiment platform for the quad rotor and the body part and the rotor structure control interface. Also, we have done some research work for the photon control for the helicopter systems. The novelty of such a method is the quantum control technology is introduced to update system parameters by using the beta information in real time to improve the control accuracy and the robustness of system. So the key point is the quantum logic model are introduced. This is a block diagram of the adaptive reconfiguration control for the quad-rotor helicopter system. This work has been published in the IEEE another transaction, Industrial Electronics. Okay, now I show some four videos of experiment result. Okay, the first one is indoor UAV formation under the fort. This is a lab. Our lab name is the photon control, or called the health monitoring management for advanced flight vehicles. So for UAV formation control, so this is the trajectory. The design one is a circle. So we inject the force with the loss of effectiveness in one UAV. You can see under the photon control, the system performance can be recovered. Second one is also indoor, but the difference is one UAV formation control with the one UGV. So this is UAV, this is UGV. I manage the ground vehicle. The formation control, we goal of this formation control is to keep the relative consistency of the position and the velocity. We will inject the force in the UAV. So inject the force and the four motors. You see there's a jump, slow motion. But under the photon control, it can be fixed up. Still keep the formation control under the force. This is experiment result. The three video. This is the outdoor, the outside, the laboratory, and still the photon control. Okay, success. This is in the Jiang campus, but no voice. Okay, so we inject forward in the first motor of UAV, and in the second motor, at a different amplitude of the fault. In the third model. In the fourth model. So all the models have occurrence of the fault in the different size of fault. So this is a simulation result of the pitch angle, yaw angle, and the fourth video is about the outdoor UAV formation. Oh, no. It's 3 UAV. So that is a 12% loss of effectiveness in one UAV. At the different size of the fault. Okay, it's me. Okay, this is 4 videos. Well, finally, about some result for the future research work. The first point is since the passive photon control have advantage of the low online computation, and the active photon control have the high efficiency. So we want to design the so-called adaptive integrate photon control to take both advantage of the two kind of efficiency method. Second topic is about the resilient control based on the adaptive control, non-linear control method to handle the structure uncertainty and structure fault. We have finished a key project about the NSF grant. The third one, what I introduced today is based on the model-based photon control. In fact, in my research team, some faculty like Dean Lu done some work on the database. In my opinion, both methods have some advantage and disadvantage. For example, for the aircraft or satellite, maybe the general model is we can be known, but because of the large envelope and the variation of the change, so maybe some parameters are unknown. So we can use the data-based method to identify the parameters. So generally speaking, we can use the hybrid model for the whole diagnosis. And in this talk, I have shown some simulation result, the visual simulation, and some experimental result. But I think it's not enough. So currently, we are collaborating with some flight control institute in China to further validate the application and the efficiency of our method. So that's all for my presentation. Thanks for your attention.
Thank you for the nice presentation. We have time for questions.
Thank you very much for the very nice presentation.
Thank you.
Yeah. So I want to ask you about the faults. So From what I understand, you assume that you have additive faults. What type of faults do you consider?
You mean which?
Even in the videos, for example, it was mentioning about 3-5% fault in the actuator.
No. This is one in the experiment. We can consider the one kind of the actuator fault, means the partial loss of effectiveness of actuator. This is for actuator fault. I think the worst case is the float, means completely lost. But this is what in the simulation or the experiment is the past loss of the effectiveness. So we use such inject some float and to test the method. Even for the worst case, the float. So this is very worst case. So sometimes for the simulation result, no problem. But for experiment, there's really problem. The system performance cannot be covered. For example, there's from the experiment, you can see when fault occurs, there's a jump. So if the worst case fault can jump out down, then the photon conjugate cannot be used or it cannot be used in time. Okay. For simulation, no problem. We can assume that maybe one actuator have full loss or complete loss. Also for experiment, for example, I have two actuators. If one actuator have full loss, maybe some problem. In particular, for the design of for FTC. So system performance cannot be reconfigured in time.
But you were not changing the effectiveness. Basically, you were doing, it was a simulated fault, right? It was.
There are two kind of fault. One is there's called soft fault. We simulate. One is the hardware fault. We also have some experiment, but not very serious hardware fault.
So in case there are sort of like dynamic faults that evolve in time, how you deal with those kind of faults?
Yeah, the second topic is about for structure fault. It's not the actuator fault, not sensor fault. So for such kind of faults, so we need to use some particular controller. For example, resilient control. This controller, the advantage is they make combination of the nonlinear control and adaptive control to handle such the so-called planned fault or unstructured fault.
Questions?
Please. Yeah.
Basically, some of the sensors also for failing together with an actuator, whether you can separate or you can identify the two.
This is related to the fault isolation. For the isolation, we have also do some research work. So we first need to isolate the fault. So, for example, which is a sensor fault or which is actuator fault, and then you use the particular the controller to compensate the effect of the fault. And in the experiment, we have inject the multiple fault, but not simultaneously. We have inject the fault. For example, the second video in the 4 models, all the models have some fault. So it means that 4 actuators have occurred fault, but not simultaneously. So in such for handle such problem, we need to the further isolation to identify the fault.
But when you have basically sensor actually it's challenging to identify. Try to take care fix the.
Yes.
Have you
Yeah, you mean for example, if your sensor fault, maybe the control design is related to the sensor, use some information. Yeah, so you need to first isolate. Yeah.
Yeah, but analyze it. Is it something that?
Theoretically speaking, I think we can do that. But in experiment, we haven't considered two kinds of fault simultaneously. Please.
I asked about the flight envelope, the segmentation, and you said that you do for control where you need to identify which in which part of the envelope you are, and then I
You mean the flight envelope? Yeah. When I discuss about the switch system, I just use the large envelope flight as an example. I mean, which kind of flight control system can be described by the switch system? Because if you use for the very large flight envelope, so if you use one model, normally you have several flight models. If you use only one model to describe, either it's too complex or it's nearly impossible. So want to classify the large flight envelope into some smaller ones according to the flight height or flight velocity into small one. For each small flight envelope, we can describe as one continuous model. So the whole system can be described as a switch system. Then so we consider the two kinds of faults. One fault is the inside each model. Each model is called the continuous fault, where destroy the dynamics of the we destroy dynamics. Another more difficult is about the discrete fault. Normally for switch system, there's a switching time or switching order. But for discrete system, we affect the switching time and switching the order. So this is the most difficult for the FDC or FTC for discrete system.
So for the spacecraft that you show in the end, you showed some pictures where there was a fault and where your direction was below the picture. So you were a single sub envelope. I mean, what kind of fault there was in that experiment?
For the discrete times, for the continuous fault, just the actual fault sensor fault. For discrete times, there's for example, there's some problem or the abnormal occurs in the switching law, so will cause the discrete fault. So in the switching law, abnormal or some this we call such behavior as a switch as a discrete fault. Because abnormal switching on time and order.
Thank you. Regarding the multi-agent formations that you showed there, I didn't understand how they exchange their states with the drones. I mean, do you have is it centralized? Is it distributed? I mean, they communicate directly. The first question is that one, and then for for the indoor scenarios that you showed, do you have a system that provides the location of each of the drones? How do they estimate their state?
So for the multiple agent system, because we use the information of the label UAV to we call the decentralize the fault estimation. Means that we use the information not only by the UAV itself, but also the UAV of a neighborhood, because some some information to change and to exchange. Use such two informations to diagnose the fault. So if we normally is not practical to use all the information. It's not practical. Use all the information to estimate the fault. And on the other hand, we use the cooperative auto control. Means use information also itself UAV and the neighborhood UAV to reconfigure the control.
Thank you for the nice presentation. My question is twofold, not directly related, but the first one relates to, have you ever investigated any faults that they are resulted by software logic rather than hardware, or the change in the physical structure of the UAV? That's number one. And how do you do that? The second one is on whether you assume any encrypted communication between the UAVs or with the ground control, whether this has any overhead.
You mean how to distinguish with the software or hardware fault?
I mean, there could be cases in the controller or software where the logic of the application, specific application of the UAV might not be functioning as it should. So essentially, it's a software fault that is not visible on the UAV as it moves. So it could be sending focus information back to the ground station, and it can range to many different effects. So wondering whether you address that in your modeling approach or data-driven approach. The second one relates to whether you assume any encrypted communication between the UAVs.
Of course, the fault cannot be visually directed. In fault detection the domain, we use the residual generation which is related to the system control, system output or the control output. So all combination of the two output area to generate the so-called the residue to indicate the occurrence of the fault. This is a fault detection. We have some logic, the residual generation and residual evaluation to detect and isolate the fault, not directly observe the fault.
Okay, thank you, everybody. Thanks. Let's thank the speaker again.
Thank you. Once again, it's my pleasure to visit here and welcome the further opportunity to visit my university many times, and welcome all of you to ideal convenient time to visit China, to visit NUA. Thank you.